structural equation model, he has calorie intake, which is your food intake, obviously, to metabolism, and he has your B weights.
What is this R squared C mean on the side of the B? On the back here.
Yeah, I see it.
On this one.
No, I see what you're talking about. I'm looking in the outline to see where it is, just trying to figure it out. Because at first glance, you would think that it would be a... I don't know. I'll ask him about it. Or make a note to myself. To email him and ask him about that. Did anybody ask in class last time?
Oh no, with so many things.
I mean, it would make sense if it were like, yeah, I don't know.
That's fine.
All right, sorry about that. I'll email it.
It's okay.
You will get it straightened out. Okay. So complementarity. So it's an interaction effect. It's the correlation between the two predictors is negative. So they have an inverse relationship.
It is the what?
So it's an interaction effect. It's the correlation between the two predictors is negative. So what you end up having is you have a high correlation between X1 and the predictor, and a high correlation between, you have a high correlation between X1 and the outcome. So predictor 1 and the outcome, highly correlated. Predictor 2 and the outcome, highly correlated. But the two predictors together, inverse relationship. So it's extremes on both ends of the data. It's also called shared suppression and cooperative suppression. Yeah.
That had that difference on it, right?
Yep. Yep, that's the one. Yeah, you'll want to look that over. So let's go to, that's also called net suppression. Redundancy. So there are two types. There's complete redundancy and there's partial redundancy. So complete is pretty rare and it's not a good thing. It basically means that your X1 and X2 are measuring the same thing. So that's two depression inventories in the same study. It's not really great.
So it means that X1 and X2 are measuring the same thing.
Yeah. Or at least you're saying you're measuring, what happens self-esteem and self-worth in the same study, and the two instruments that you're actually using are measuring the same thing. They aren't parsed out very well. They don't define actual differences between these two different things, right? These two different concepts. So what you're getting is the same data on the same concept, right? It's not a good thing. So your beta weight goes down a lot, basically, is what happens. And then your partial, this is more common. This is kind of what happens mostly. It's every time you add another predictor, it takes away from the outcome and the other predictor. So your B weight is going to go down slightly as you add in more predictors. Your adjusted R square is going to go down a little bit as you add in predictors. So as you add in more predictors to explain why, there's a relationship between all of them. So not only are you eating away at the variance of y as you add in more predictors, but there's also some overlap a little bit between the predictors themselves, right? They're not completely independent, so they begin to eat away at some of the variance of each other, right? So it's kind of like a shared little prong in the predictor.
You said every time you add another predictor, it takes away.
Yeah, it takes away from the outcome and the other predictor. So it takes away a little bit of the variance. So your B weight is going to go down a little bit as you add in each predictor. Your adjusted R squared is going to continue to go down slightly. It's not going to do something drastic, but it's going to continue. You're going to just see a general decline as you add in more predictors. So singular matrix, it's a way of looking at multicollinearity. It's basically meaning that enough of the correlations combined equal 1, which is the extreme of multicollinearity.
Can you repeat that?
Yeah. So a singular matrix, it's the way of looking at multicollinearity. And basically it says that enough of your correlations combined equal 1, which is the extreme end of the multicollinearity spectrum.
It's the way it looks at collinearity.
Yeah, and so enough of your correlations combined equal 1, which is extreme. That is multicollinearity, when your enough of your correlations combined equal 1. It's extreme multicollinearity.
And multicollinearity is bad.
No. It's basically there's too much overlap. Let me see. I believe you're. Really wish I had a book. Which is the problem. It's. So you have your collinearity statistics. That was the tolerance and your BIF. And again, for the tolerance one, the higher the better. On the BIF, the lower the better. I believe the BIF as it goes towards 10. Not a good thing.
Yeah.
But that's the one that's in your book. And that's overlap with predictors. We don't want that. Okay, path diagram, did he go over the types of variables, endogenous, exogenous, in last class?
I don't remember.
Jenna did.
Jenna did, but I don't think he did. But it's good to know.
All right. So in a path diagram, you have a different types of variables. And basically the difference is which arrows are going to it and going away from it. So that's the big difference. So endogenous variables are variables with arrows going to it.
Those are the ones that go in.
Yep, arrows going to it. So on a particular regression, that's the one that's going to be used as the outcome. And so you can have multiple ones in a path diagram, but it's whatever arrow is going to it is labeled as an endogenous variable. Endogenous variables also get error terms that go to it. This is something you'll see in Amos, but just know the ones with arrows going to it get error terms. If you didn't go over it in class, you don't need to know the specifics of it, just kind of keep that in your mind. Exogenous variables are variables with arrows going away from it. So again, exogenous within an EX, variables have arrows going away from it. And then covariates have double arrows. So it's kind of like a back and forth.
Does that mean there's one going to it and one coming out?
Yeah, it has both. That's basically so there's something saying that you have, this is a covariate relationship. This is an endogenous variable. And then this would be the exogenous variable. That kind of doesn't make sense because it's kind of multiple things, but you get the idea. If these two variables have arrows doubling back and forth, it's a covariate relationship. If you have now this, so arrow going to it is what? So this would be your endogenous variable. An arrow going away from it, so this would be your exogenous variable. Okay.
Okay, it's only to say covariate if it's the double arrow, not if there's one coming in and out on the other side. Like
Right. It can be both, because you're going to have,
because I mean that one has like one coming in and one going out.
So that could be covariate.
yeah. Well, it's typically when the relationship is shared between it. So it's like the back and forth. So this one isn't a covariate, but it's when two variables together have this, right? So there's no start or end, it's kind of a continuous loop. So basically what you create is a circle. As one goes in, this is going to predict this, and this is going to predict, you know what I mean? It's a continuous feedback. Where this is kind of not the same thing. You've got incoming messages, it gets filtered through, and then it comes back out this way. It's kind of not the same thing. So the one on the left is the covariate. Covariate?
Yeah. You want to work with one of these weight loss exercise, calorie intake?
Yeah, so let's add muscle mass to it. Right? So what is it? And the hard thing about path diagrams is where the location of your variables in a path diagram is what counts. So you can't just like place them randomly. So when I do the spur of the moment thing, it's not gonna probably make sense as far as the full path, but I'm gonna try. So, this is, okay, and then, so this is your metabolism, weight loss. Let's say you added a third variable of like muscle mass. Okay? Well, there's a direct relationship between the amount of muscle you have and how fast your metabolism is. The more you add muscle mass, the faster you're gonna have, the faster your metabolism is going to be. And then it's the same thing. Well, then the more muscle mass you have, the more you're gonna be able to lose weight because you have more faster metabolism. So if you were to add, so it really doesn't make sense when we talk about weight loss, but if you talk about the relationship between these two variables right here, this would be a covariate type relationship, right?
Okay.
Because there's a continuous feedback. These two things are directly related.
Okay. Yeah, okay, thank you.
Okay. Okay, this is going to be a good one. For one-sided arrows, you want to look at the beta weights. That's where you get the information. For two-sided arrows, look at Pearson correlation. So for covariates, you can just look at the Pearson correlation table. Did he talk about parameters and observations? Did Jenna talk about parameters and observations on Wednesday? Okay. So parameters are basically a way of getting your reproduce correlations. So the idea is you want whatever your parameter set, your model, to not be greater than your observations. So your parameters, the equation is path plus covariate plus endogenous, or sorry, it's your path plus covariate plus exogenous plus disturbances, which are your error terms.
Can you write that?
Yeah. I feel like I'm giving you too much that he hasn't even started to go over, so this might get more confusing than anything else.
Yeah, it's not really on the thing.
Yeah, I don't see it. All right, I'm going to skip this little section of it because then I'm introducing a lot of terms that he hasn't even talked about, like your disturbances, which are the errors. So we'll hold off on that piece. Just remember, you want your parameters less than your observations. I think that should be sufficient. So let's go over reproduced correlations. So basically, it's a way of checking how well your model fits, right? This is like your residual regression, or your residuals on your, in the unit we discussed last, where you want your errors obviously to just be small because you want your predicted to be the same as your outcome, pretty much. Yeah. So it's basically the same thing, same concept. You want to make sure you're making as little error as possible with your model, and the way to tell is to see, does your model predicted values match the actual values? Okay. So that's what your reproduced correlations are going to check. So it compares computed to the Pearson correlation table, and your kind of golden number is you want it within 0.05 difference, right? So no more than 0.05 and no less than 0.05
So it should be
between your predicted and your outcome. Yeah. So if you were to have your predicted score and you were to have your outcome score and you subtract those two numbers together, if the difference that you come up with is greater than 0.05, your model doesn't fit that well. Or at least it's not ideal, right? Does that make sense? So if you have a difference of 2 between what you predicted, what your model predicted the number to be, and what the actual was, well, your model's not really fitting then. Something's going on, you need to readjust your model. So you do that for each one of them.
For each outcome, each predictor?
Each path.
Each one, okay.
If each one.
Oh,
you
that's
report.
when he did the R12 or P12 and he did all the...
All of the long map, yeah.
Okay.
Where's that on my old bed?
He doesn't have it on this output, he did it in class, that's when I left. It's something
Yeah.
you check, you check it with your Pearson correlation table. So you run your regressions, you get it all, and then you look back at your Pearson correlation table to get the actual computed values. Okay. Okay. So causal arrow is the path analysis arrow to the variable is one-sided. So basically when you have, like here, if I were to have food going straight to a weight loss, well, that's saying there's a causal relationship. The amount of food that I eat directly influences my weight change, right? That's a causal relationship. So,
Sorry, can you repeat that?
yeah. So it's in a path analysis, the arrow going to it, it's one-sided. It's saying there's a causal relationship. You're saying this predictor is going to directly influence the outcome. Okay. So mediation. It is tested using the Sobel-Preacher test of mediation. Obviously, you're not going to forget what concept the Sobel-Preacher test is going to capture.
It's tested using the...
Yeah, it's tested using the Sobel-Preacher test of mediation. So basically, A and C only have a relationship because of B. Is the idea.
Why? Say it again.
So it's A and C only have a relationship because of B. So basically, B is facilitating the relationship between A and C. It's kind of like a puzzle, right? You've got half of the puzzle here with its A, you've got the other half of the puzzle C, but then you've got all these missing pieces in the center. It's basically saying there's another variable that's going to link those two sections of the puzzle together. Okay. So it helps to explain the relationship is another way to think about it. So in ANOVA, or a moderator, so you got a mediator and a moderator. A moderator is actually tested through an interaction in ANOVA. If you remember your interaction, it's your A times B times C, whatever that, right? First semester. It's not causal. So it basically changes or alters the relationship between two variables, but doesn't explain it. So you want to actually use this concept first before you jump directly into mediation. But if you have, we want to draw a picture of the two concepts. You have so this is A, and this is C. What's happening in mediation is B is facilitating this relationship between these two things, right? So it's A and C have a relationship because B plays a role. In moderation, you've got A has a relationship with C, but B somehow affects the relationship. Doesn't facilitate it, it just changes the relationship. So that's typically what a moderator is. And a variable that is added that changes the relationship between two variables that pretty much that do already have some sort of relationship, right?
So in that one, you said A and C have a relationship, and B affects it?
Right. So if you were to say A and C this were attendance and exam score, right? Attendance has a relationship with your exam score, but let's say B is time spent outside of class on the exam. It's going to affect the relationship between these two things, right? Okay. Types of regressions. So the goal in your regression is you basically want the least number of predictors to explain the most amount of variance. Which makes sense, right?
Can you repeat the last part to explain the most?
Yeah, so we want the least number of predictors to explain the most variance. So if we can explain 80% of the variance of a particular outcome using 3 variables, we want to take that model instead of the 7 models that are used to explain 85% of the variance, right?
What's the term for that one?
These are just looking at types of regressions. So you've got stepwise, which is good for explanation. It's bad for hypothesis testing. It's basically your computer's determining the best order of entering variables beforehand, then uses steps to add and remove variables. So this isn't theory driven, this is computer driven.
And that's the one you said is bad to get the outcome and then change your subcode.
Correct. This is more like if you're not doing an actual research test, if you're in a corporation and it's like you're looking at productivity, it doesn't matter how you get to what is the most productive workflow as long as you get there, right? Because that's ultimately the goal. The goal is lower cost. We're not concerned with publication. We're not concerned with ethics or integrity. It's just like we want to make sure our costs are down. And so we're going to plug all these different variables to figure what's the best workflow for that. So the computer will adjust it and say, okay, well, this method is the best one, so this is the one you should input. But if your intent is to publish and say, okay, well, I'm looking at the literature, and this is what all of the literature up until now says on this particular concept, so this is how I'm basing my theory, and this is what I'm saying, okay, given till now, what we know about these two, the relationship between these two things, this is what suggested, this model that I'm creating is what suggested. Then you want to put in the, input yourself in the order that the order of your hypothesis, as opposed to letting the computer go, oh, well, I'm going to change that, even though it's not supported by the literature. Does that make sense?
Yeah.
So hierarchical. So it's not that it's one is bad or good, it's one is they're used for different things, right? It would be bad only in the sense if you change your dissertation to match the computer output.
And how bad would that be exactly? What does that mean?
What does that mean? It probably amounts to an ethics violation, which means that they would probably terminate your standing. You would get fired from school, expelled, I think it's the word. But I wouldn't call it plagiarism, but it's an ethics violation, and I think that's still an expellable offense.
So it's like, you have to report that it just didn't work,
Yeah.
pretty much.
Yeah. Now, let's say you report that it didn't work, and then your advisor has you see, okay, what does work, and then saying, okay, well, this is what we did. It's about integrity, though. This wasn't my theory, but this is the thing that happened, and maybe in a discussion section listing that and saying, okay, where is the void in the literature so that model wasn't generated, that I wasn't able to generate that model based on the present literature, so you can kind of hypothesize about where future researchers should go with that, but yeah.
Okay.
I mean, it's still used to some extent, but yeah. To say it was hierarchical, but it was really stepwise, that part. Simultaneous is all predictors, all added at once.
Wait, did you already go with hierarchical?
Yes, it's variables entered by researchers based on theoretical assumptions. So you're basically saying out of the equation that he gave you, so if you were doing stepwise, the computer would throw all these variables in and generate it would basically go in order of what variable accounts for the most variance and then go down from there in weight loss, right? But in hierarchical, you would say, well, I think no matter what, it's food intake. I don't think your metabolism really matters more than food intake, and I don't think exercise matters more than food intake. I think food intake overall is going to count for the most amount of variance in this model. So that's the one you choose to enter first. And then you say, okay, well, based on exercise and metabolism, which is going to go next? And I think it's going to be metabolism. And then you would then input exercise as your third variable in the predictor. That's hierarchical. So yeah. So simultaneous is you're just done from all in at once. And then predictive is not concerned about order, but it's only interested in predicting the outcome. So you don't really care which one's most important. Your goal is just to account for all of the most amount of variance that you can.
Which one's that one?
Predictive.
Okay.
So again, it's not really the order that matters. You're just looking for how much of the outcome can we reasonably predict. So it's just about total amount of variance that then is captured. Okay. So partial correlation.
You go over direct effect and indirect effect, all right?
I didn't go over it, but I have it on, I don't have it online. Oh. Okay. So direct effects are when you're able to take the beta weights to compare the, so like on your reproduce correlations. So direct effects and indirect effects directly determine how you're going to compute the numbers you're going to use for your reproduce correlations, right? So direct effects are when you can just actually take the beta weight and compare it directly. So it's the one where it's just the arrow going straight to, right? You've got a box and then the arrow goes straight to it. There's no additional variable in that relationship. Indirect effects are when you need to multiply the beta weights in a path towards something to get the value. So in that one, it was, remember, he needed to go through exercise to food intake to get the beta weight for weight loss, to calculate that. So indirect effects are when you have to multiply two paths by each other, those two beta weights by each other.
How is that different from mediation?
Or just a calculation?
This
Mediation
is just the calculation for the reproduce correlation. So in your path diagram, to figure out what your overall correlation is between exercise metabolism and weight loss, well, you would want to multiply the beta weights together to get that path. Does that make sense?
So the mediation part is just describing it out, and the other one's calculating?
Yeah, one is, I mean, mediation is more like you're actually using it to explain the relationship. It's more of a conceptual thing. This is testing your model fit. And so this is producing the numbers to determine how we're going to test our model. And if our model is a good enough fit for the concepts, right? What time is it?
57?
Huh?
57?
Partial correlation. It's correlation after the statistics removes or subtracts the linear effect of the variables.
Remove the what?
Hold on, let me find a better way to say that. So partial correlation is basically partialing out the variance from both the outcome and the other predictor variables.
What does that mean, partially calculated?
So it's basically purifying the relationship between x2 and y by taking out x out of both, x1 out of both x2. That makes sense. It's removing some of the correlation that's, so let's say that again. It's partialing out the variance from both the outcome and the other predictor variable.
So that's taking out the overlap of the two x's, is that what that is? Is it taking out the overlap of the whole? Or is it disconnecting the x? I guess that's where partial and partial.
Right. It's It's basically, it's actually removing it. So where, that's the part column, wait, no, that's the partial column, right?
Yeah.
Yeah.
It's the one that's not, we don't very often. So it's the partial column, and basically what partial is doing is it's actually removing some of the variance out. So it's partialing out the variance from both the outcome and the other predictor variable to get the idea, to get the relationship between predictor one and the outcome. It's removing any of the other variables that are present in the equation, trying to remove that out. Versus semi-partial, which is the part correlation, the part column, the one next to it, is the unique variance accounted for by that particular variable, and it's holding constant the other variable. So it's not removing, so it's basically removing the variance from the other outcome, but not from the other predictor variable. Whereas the partial column is removing some of the variance from both the outcome and predictor to get the value.
So,
Looking at the circles, can you draw them so we can see visually? Partial and semi-partial.
Okay, let me try this. Okay. So this is your part column, right? Oh no, your partial. And basically it's saying to get the variance of this predictor, it's going to remove the variance from the outcome as well as the other predictor, right?
so it ditches the y and the x2.
Right. That's what it's doing. It's removing some of the unexplained variance from both the outcome and the other one. So
Okay.
it's kind of like subtracting it out. Versus in the part column, what it's saying is you've got your y, your outcome, you've got your x1 and your x2, right? It's saying, well, it's going to remove some of the unexplained variance from the outcome, but it's going to hold this constant,
Okay.
or the other, and then all the other predictors. It's going to hold this one constant. So it's not actually going to subtract anything out. It's not going to remove anything. It's just going to hold it there, and right? So that's what the partial, semi-partial column is. The part column is.
Okay.
So, and he will label it as unique variance accounted for by that particular variable while holding all other variables constant. Sorry. That's your part column. And you want to square this value for a percentage to see how much change this one variable accounts for. Okay. So let's go on dummy variables. And it's basically a way of coding variables. They're coded dichotomously, so you got 1 and zeros. 1 equal yes, 0 equals no. And you use this for categorical variables, like let's say you have ethnicity. And if you were to put them all in one column and you had 5 ethnicities that people could option, and then you label them 1, 2, 3, 4, 5, we are giving nonsensical numbers that do have actual kind of meaning. So then whoever is in the 5 category, whatever ethnicity that lands up there is going to account for more, when really doesn't account for any more or any less than the other ones. It's just a classification kind of variable, right? So you would then put them into each separate columns, and agreement with one means there's no agreement with others, and so it balances out. So it's just a way of coding variables, so you don't give more meaning than is due to a particular variable.
So if you did the 1, 2, 3, 4, 5, it would kind of mess up with the order.
It would mess up with the order, but then you would also have more value placed on the people in the 5 category,
Yeah.
when it's just a classification variable.
Okay.
That category doesn't mean any more than the other ones, right? But if you have so you code it as 1 to 0, or 1 or 0, like a yes or no, and then you separate them all out. So as opposed to having a category that's ethnicity, you would actually write out categories. So white, Asian, African American, yeah, Filipino, whatever ethnicities you're listing in your study that you're testing, and then agreement with one would be you have 1, and then you would zeros in all the others, right?
Yeah.
So it's just you're testing 1 zeros. So yeah,
So you would have like one column and like the first cell would have 1 and the rest would have 0 for that
Right.
row. And then the next one would be 0, 1, 2.
and right, and you do the same thing with gender.
Okay.
So as opposed to putting gender in a particular box, typically what you'll see, because if you were to do gender, you would have women being, you could do it with women being 1 and men equal 2, right? Well, as you get more men into your study, 2 adds up really quickly, right? But 2 and all the 1s together, it's going to create like a difference. You're going to see variance basically where it's really not that. That's not what it is. It's a category. So what you do then is you have women in one column, men in another, and agreement in the women column means that they're going to have a 0 in the men column, and vice versa. So it averages out over time, right?
But there are some instances where you can do that. You can have one column, you put it 1 or 0, 1 or 2, whatever.
Yes.
And why does that not work here, and where does it work?
It depends on how many the variables go into that agreement or not column. But it's more like tricks in SPSS. What you really want to know is dummy coding categorical variables as 1s or 0s. Okay. But that's like a trick for SPSS, and I'm like trying to rack my brain to think about an example that I could give you. We could put them all in and 1 and 0 and it worked.
Can you just explain from the last one, explained variance? I can't remember.
Explain variance.
It's from the other exam.
Oh, yeah. It's the proportion of variance explained when predictors are independent.
Proportion of variance
Uh-huh.
when predictors are independent.
Yep. It's the portion of variance explained when predictors are independent.
Dependent meaning the one that's like the circle here, one here, one here. They are not.
Yep. For 2 predictors, no overlap. It's that portion of explained variance.
Oh, so you have like, so you have X and Y, and then X2, and X, the X's would be overlapped, so it explains some of the variance, but the Y would, and that would be independent.
Is it that it's
That's what it looks like?
It's the relationship between the 2. So you've got Y, and you've got X1, and X2.
Oh, okay.
So you know exactly that overlap is from X1 and the other one is from X2.
Yeah, so complete independence between the predictors, right? But there's still overlap. That's looking at this portion. What is this explain variance here? Because there's almost like an indirect relationship. Well, then X1 and X2 might not have a relationship together, but they have a relationship in the sense that they explain a similar phenomenon.
Yeah.
They're both causing something to happen for this particular outcome.
And that's the only situation that this is explained variance.
Yeah, it's just looking at, well, what is this explained portion right here when the two predictors are independent? And I think that that's it. I have,
Can you go over the Sobel picture? Means that this is a test for mediation, or do you need to know anything else about it? What-
no, just that it tests mediation and what mediation is. Yeah.
Is there a number? It's on the output, right? Is there a number that we're looking for?
Is there a number that we're looking for?
Yeah, on the Sobel feature test.
Where is it on your output?
Isn't it
I'm
just
just
in the
wondering.
other kind of the other program, the Amos?
Did you go over Amos last time?
Kind of.
Yeah.
Damn it, I missed it.
He has a handout for it.
All right. No, I don't remember that. We didn't go over, actually, the stuff you guys are gonna go over for Amos is completely new this
Yeah,
semester.
I think he
He
just
just showed
mentioned,
it,
but it's
yeah.
not.
Okay. Yeah, for this test in last semester's class, all we need to know is what solo creature tested, basically, what it looked at, and that was mediation. You can always look at your book to see if there's
Yeah.
a value attached to it, like a range.
Uh-huh.